All right, CUET aspirants, you ready for this? We're about to tackle one of the trickiest topics in organic chemistry, but we're going to make it easy. Today, we are breaking down the physical properties of haloalkanes, and I promise by the end of this, you'll know exactly how to lock in every single mark from this section on your exam. So let's get right into it.
Okay, be honest. Did those questions comparing the boiling points of, say, N-butyl chloride, sec-butyl chloride, and tert-butyl chloride totally make your head spin? Yeah, you are definitely not alone. It's a classic confusion spot. But you know what? Stick with me for the next few minutes, and I promise you, these are going to be the questions you hope to see on your exam paper. Seriously.
So why are we focusing so much on this one topic? Simple. It is an absolute goldmine for your CUET score. The exam is filled with comparison questions from here. You know the ones, which has a higher boiling point, or which is more soluble. And the best part? Once you get this simple logic we're about to cover, these questions turn into easy, guaranteed marks. It's like a cheat code for your final score.
Okay, first things first, before we get into all the tricky comparison stuff, we have to start with the basics. So, Section 1, the fundamentals. Let's make sure we're all on the same page about what a haloalkane actually is. It's actually super simple. Just picture a normal alkane. Now, imagine you just pluck off one of its hydrogens and swap in a halogen instead. Fluorine, chlorine, bromine, or iodine. Boom, you've got a haloalkane. But what's the most important word you see here? It's polar. Seriously, burn that word into your brain. This one idea is the key that unlocks pretty much everything else we're going to talk about today. All right, so we've established that haloalkanes are polar. Now let's see what that actually means for their properties. We're on to the main event here, decoding boiling points. Pay close attention, because this is a huge favorite for exam setters. Okay, first up, let's put haloalkanes in the ring with their parent alkanes. Who's going to have the higher boiling point? Well, it's the haloalkane. And it's not even a close fight. It wins every single time. And here's why. There are two big reasons. First, like we said, they're polar. It's like their molecules have these little built-in magnets, creating dipole-dipole forces that stick them together. That's way stronger than the super weak forces holding alkanes together. And reason number two, adding that heavy halogen atom increases the molecular mass, which basically gives those intermolecular forces an extra boost. Now get ready for a classic exam trap. This is where so many students go wrong. If you look at this trend, your brain might tell you, hey, the carbon-fluorine bond is the most polar, so it should have the highest boiling point, right? Wrong. Absolutely wrong. In this specific battle, molecular mass is the undisputed heavyweight champion. Polarity doesn't stand a chance. Iodine is the heaviest halogen, so it gives Ri the strongest van der Waals forces and the highest boiling point. I'm telling you, remember this forever. For this trend, mass completely dominates polarity. Got it? And that brings us to another huge concept, branching. The easiest way to think about this is with a picture. Imagine a straight chain molecule is like a long, straight log. It's got a huge surface area, right? So other logs can stack up against it really well. Now, picture a branched isomer. It's all scrunched up, more like a ball. It has a way smaller surface area, and less surface area means less contact, which means weaker forces between molecules. And weaker forces mean a lower boiling point. It's that simple. That's why the log, N-butyl chloride, will always have a higher boiling point than the ball, tert-butyl chloride. Awesome! We've totally cracked the code on boiling points. Now let's power through the other key physical properties they love to throw at you on the exam: solubility, density, and dipole moment. Okay, let's talk solubility. This one can be a little tricky. You'd think, okay, haloalkanes are polar, water is polar, they should mix, right? Well, not really. They're only very slightly soluble in water. Think of it this way. Water molecules are like a super tight-knit group of friends, held together by really strong hydrogen bonds. For a haloalkane to dissolve, it has to break up that strong friend group. And the new, weaker friendships it forms just aren't worth the energy it took to break the old ones. It's just not a good deal. But when you put them in an organic solvent, where the friendships are about the same strength, they mix perfectly. Just remember the golden rule of chemistry. Like dissolves like. Next up is density. And honestly, this one's a breeze. The rule is super straightforward. The heavier the halogen, the denser the compound. That's it. Notice how it's the exact same trend as boiling point. It's all about that increasing mass. And here's a really handy fact for your exam. The lightweights, so alkyl fluorides and chlorides, they're generally going to float on water. But the heavyweights, the bromides and iodides, they're denser, so they're going to sink. Easy marks right there. All right, let's get into dipole moment. But before we look at any examples, I need you to remember one crucial rule. Say it with me. Symmetry kills polarity. If a molecule is perfectly symmetrical, it's like a game of tug of war where all the teams are pulling with the exact same strength in opposite directions. What happens? Nothing moves. The individual bonds can be polar, but all those little pulls cancel each other out perfectly, leaving you with a net dipole moment of 0. And here is the absolute perfect example of that. Just look at carbon tetrachloride, CCl4. You've got 4 polar carbon-chlorine bonds, all pulling away from the center. But because the molecule has that perfect symmetrical tetrahedral shape, it's that perfect tug-of-war game again. All the forces cancel out. The result? A completely non-polar molecule, even with polar bonds. But now look at chloroform, CHCl3. Just by swapping one of those chlorines for a hydrogen, we've broken the symmetry. It's like one of the tug-of-war teams got weaker. Now the poles don't cancel, and bam, you get a polar molecule with a real dipole moment. It just goes to show you, geometry is everything.
Okay, theory time is over. Now for the most important part. Can you actually apply this stuff when the clock is ticking? It's time to find out. Welcome to the CUET exam practice zone. Let's see if you can spot the traps I've set for you.
But first, I've got a little memory trick for you for that super important boiling point trend. Just remember this silly little phrase, I bring clay for. See? The first letter of each word gives you the order from highest boiling point to lowest. Iodine, bromine, chlorine, fluorine. Say it out loud right now wherever you are. I bring clay for. It's kind of goofy, but trust me, it works.
All right, question number 1. Take a look. We're comparing 4 different isomers. The question is simple. Which one has the highest boiling point? My hint to you is think about surface area, the log versus the ball. Okay, pause the video right now, figure it out, and then hit play when you've got your answer. Go on, pause it.
Okay, are you back? The correct answer is A, N-butyl chloride. Did you get it? It's because it's the straight chain isomer. It's our log. It has the biggest surface area, which allows for the strongest van der Waals forces. All the others are more branched, more ball-like, so their surface area is smaller and their boiling point is lower. Simple as that.
Okay, let's ramp up the difficulty. Time for an assertion reason question. These can be tricky. The assertion A is CCl4 is a non-polar molecule. The reason R is the CCl bonds in CCl4 are not polar. Now think carefully. Is the assertion true? Is the reason true? And is the reason the correct explanation for the assertion? Pause and think it through. All right, the answer is assertion A is true, but reason R is false. This is such a classic exam trap. Yes, CCl4 is absolutely a nonpolar molecule, so statement A is correct. But why? It's not because the bonds are nonpolar, they are definitely polar. The real reason is that perfect symmetrical geometry we talked about. The one that makes all the individual bond dipoles cancel each other out. So the reason given is just flat out wrong. Okay, everyone, listen up. I need your full attention here because this is critical. I'm about to give you the 5 biggest traps that students consistently fall for on this topic. Number 1, blindly thinking that higher polarity always means a higher boiling point. We know mass can dominate. 2, completely forgetting how branching shrinks the surface area. 3, making the blanket assumption that all haloalkanes are denser than water. Remember, the lightweights float. 4, forgetting that symmetry kills dipole moments. And 5, getting confused about why they don't dissolve well in water, but do in organic solvents. Seriously, if you can just avoid these 5 mistakes, you are already way, way ahead of the competition.
Whew! We have covered a ton of ground. So let's do a final super fast revision to lock all this information into your brain for exam day. You ready? Let's go.
Here we go, the entire topic on one slide. Let's do this fast. Boiling points, higher than alkanes because of polarity and mass. The halogen trend, Ri is the highest, then RBr, RCl, Rf. It's all about mass. Chain length, longer chain, higher boiling point. Branching, more branches, lower boiling point. Solubility, terrible in water because of H-bonds, great in organic solvents. And density gets heavier as you go down the group. Boom, that's the whole topic in less than 30 seconds.
So, how did you do on the practice questions? Drop your score in the comments below. And more importantly, let me know what concept was the trickiest for you. Was it the branching thing or the dipole moment trap? Your comments actually help other students who might be struggling with the same thing. Look, if you can master this, you are one huge step closer to getting into your dream college. In the next explainer, we're going to tackle the chemical properties, which is a whole other beast. So make sure you're subscribed so you don't miss out. You're doing great. Keep up the hard work.